May I ask you to take your seats? We are about to begin. Ladies and gentlemen, welcome at the Faculty of Physics, University of Warsaw. My name is Krzysztof Turzyński. I'm the Deputy Dean of the Faculty of Physics, and we are here at an event that's a part of an Ask a Physicist series. This is a series of our outreach activities that's coordinated by Professor Piotr Sułkowski, and this consists of two lines of activities. The first one are the lectures by distinguished guests that tell people from everywhere in Warsaw and everywhere around the world, if we have online transmissions, how physics works and why it is exciting. And another branch of our activities consists in actually answering questions that people ask us online through our special form. So we have a very large library of the answers to various questions regarding complicated things and also everyday physics. So if you haven't seen this library, I really encourage you to use its resources, because it may contain the answers to many questions that you always wanted to ask but were afraid of. But without further ado, let me ask Professor Piotr Sułkowski, the coordinator of the series, to introduce our guests for tonight.
Thank you. So it is my pleasure to introduce William Magwood, who is a Director General of Nuclear Energy Agency. It is one of the agencies in OECD. And he has held this post since 2014. Before that, he was a commissioner in the US Nuclear Regulatory Commission. So as you may see, most of his life, I suppose, he was involved in some issues related to nuclear energy. But not only that, because he has degrees in physics, but also in English and also in fine arts. So he has a broad horizons and experience. And the lecture he will give today is the 21st Century Nuclear Resurgence, Opportunities and Challenges.
Thank you very much. Can you hear me? Loud and clear? In the back? You can hear me? No problems? Okay. Not really. Turn it up. Better? Better? Okay, perfect. Well, good evening. Good evening. Good evening. All right. Good, you're awake. So, this is a real pleasure for me. This is not my first visit to Poland, but it is my first visit to the University of Warsaw. It's long overdue. I've heard about the university for a long time, but this is the first chance I've had an opportunity to make a visit, so it's good to see all of you. There's many of you here, and most of you are physicists, I guess. Is that right? Yeah? You know, physics is the only real science, right? They told you that, right? Well, actually, there's two. There's physics and psychology. Everything else is derivative. And as physicists, you're supposed to explain to the rest of the world what's actually going on. So I'm here to tell you a little bit about what's going on in the nuclear sector. A lot's been happening. But first, let me tell you a little bit about myself. I am, as you heard, before coming to the Nuclear Energy Agency, which I'll talk about in just a second, I was a commissioner with the U.S. Nuclear Regulatory Commission, so it's one of 5 people appointed by the President to oversee nuclear safety in the United States. So I did that for 4 years. Before that, I ran the U.S. government's nuclear energy program. So I was responsible for everything with civilian nuclear energy in the U.S. And I did that for a total of 11 years, which is a lot longer than any sane person would have done it. Before that, I worked in the industry. So I've kind of seen this nuclear sector evolve over a long period of time. And I can tell you that right now, today, and during my career, I don't think there's been a more exciting time in the nuclear sector. And I'll tell you why. First, the NEA. So what is the NEA? More of you probably are familiar with the IAEA, which is located in Vienna, which is a UN organization with 165 member countries. The NEA is much, much more specialized. Our members there are 34 countries, and our members are, in general, the countries with the deepest experience in nuclear safety, nuclear regulation, nuclear science and technology, research, law, really all the areas of civilian nuclear technology. So we are the experts. In the discussions that take place at the NEA are really at the expert level. The NEA has about 3,000 people right now today that are doing some activity under the auspices of the NEA. And much of what we do is producing reports that are available free of charge to anybody who wants to download them, covering the range of activities that we do. Obviously, in recent years, one area that has become very important to our member countries is to deal with the climate crisis. Climate crisis has been going on for quite some time. When I was at the Department of Energy, where I ran a nuclear energy program, we were talking about the climate issues back in those days. And when you look back over that period of time, it's amazing how little has actually gotten done. When I look at where we are today with climate, what I see is a world community that seems to be getting more serious about the issue, but it's probably 20 years later than it should have started if it was going to meet the objectives. The scientists want to try to keep global temperatures from rising at 1.5 degrees above pre-industrial levels. I will tell you that I think that is going to be not just very difficult, I think it's going to be incredibly difficult at this late stage. It's just a very, very late start. We are starting to moderate some of the growth. You can see the different scenarios in this chart. I don't think we'll be at the 5.4 degrees C or 5 to 8.5 degrees C. I don't think we're going to be that high, but to meet the 1.5 is going to be extraordinarily difficult. So as the world has looked at this, and we've seen countries setting their targets, and most of our members have set this target to have net zero emissions by 2050. They've been saying that for quite some time, really since the Paris Accord, which is now about, 5 or 6 years ago. And the missing element in that conversation was, how are they going to get there? And I will tell you, I have traveled around the world. I've met with many ministers and experts in different countries. And when you close the door and you sit with a minister and you say, so minister, your country has declared that it will have zero net emissions by 2050. How are you getting there? The ministers almost invariably will say, oh, we don't know that yet. Well, okay, if you don't know that, then how are you going to get there from here? Because 2050, in real terms, I know for those of you sitting in a room, many of you are in your 20s. 2050 sounds like a long time from now. When 2050 gets here, you're going to say to yourself, boy, that happened fast. Time goes very quickly. You're talking about the kind of industrial change we're talking about. You're talking about building more nuclear plants. It can take a decade to build a nuclear plant from beginning to end. So the time is very, very short, and it's getting away from us. But what we have seen in recent years is that people are starting to take seriously the how do we do it. And this chart is adapted from the IPCC, the International Panel on Climate Change. And what the International Panel on Climate Change did in a report that came out a few years ago was they looked at 90 different pathways, 90 different approaches that could be taken to reduce CO2 emissions. And we looked at this report, came out in 2018 actually. We looked at this report and we found something really quite interesting. And that is that if you look at these 90 different scenarios from different institutions, you can see on this chart the IAEA, the International Energy Agency, Shell Oil, Bloomberg, there were 90 different groups that did their analyses, all independent. And what we saw when we looked at this was something quite interesting, that in almost every scenario from all these independent groups, nuclear was a major factor. And this was happening despite the fact that when you went to international meetings where ministers would get together and talk about climate change, and I went to many of these meetings, ministers never talk about nuclear energy. And I said, well, there's a disconnect here. The experts, the analysts are saying nuclear's got to be a big part of it. Ministers never talked about it. So we look at this and we discovered something kind of interesting, that if you do, this is really complicated math, take an average of what all these scenarios say about nuclear. On average, they said that nuclear has to triple from where it is today to meet the 1.5 C. All different scenarios. Some of them had massive increases for nuclear, far beyond 3 times. Some were more modest, but on average, it was a tripling. And so when I saw that, I asked my staff, I said, so we think tripling, and we actually did some independent analysis, and we came to a similar conclusion that tripling is about right. But the question is, how do you get there from here? You know, this is essentially the mid-20s, right? So you're talking about something in order of 25 years to make this big, massive nuclear construction. Is it possible? Is it physically possible to build that much nuclear capacity? And the answer we came up with after looking at this for some time was, well, if it is possible, it will require the use of basically every arrow in the quiver. We will have to keep existing plants in all long-term operation. You know, there's about 400 reactors in the world today. The largest component of non-emitting capacity on the grid in OECD countries today is nuclear. If you don't keep those plants, you're not just getting closer to the climate targets, you're actually falling behind. And there are countries, as you know, that have shut plants down. That will be regretted in the future globally. We also have to build new large Gen 3 plants. And of course, Poland is one of the countries that is actively pursuing the construction of large Gen 3 plants. We also will need to build small modular reactors, and we will also need to look at non-electrical applications. So let me look at each one of these briefly. Long-term operation. So long-term operation used to be somewhat controversial. In some countries, there is the belief that a nuclear power plant lasts 40 years. And after 40 years, suddenly, miraculously, it becomes too dangerous to operate. There is that legal philosophy that some countries have. This is wrong. This is inaccurate. This is not based on any technical fact whatsoever. A nuclear power plant can operate as long as you maintain it and as long as you take care of it. The only parts of a nuclear plant that are difficult to replace are the reactor pressure vessel and the containment building. Other than that, everything can be refurbished, everything can be replaced quite straightforwardly. And if you look at plants that were built in, say, the early 1970s, those are physically not the same units that were built in the 1970s today, because so many things have been upgraded and replaced over the years that they look like the same plant, but they're not the same plant. And so we believe that there's no reason why today's nuclear plants can't stay online for a long time. And many more countries are starting to come around to this. And so the 40 years has given way to more of a 60-year average among most of our members. And in the case of my home country, the United States, people are already making applications for 80 years of operation. And there's people who will whisper about 100 years, but they don't want to bring that up quite yet. But there are people I know that are absolutely convinced you can operate these plants for 100 years. Losing these plants, as you can see here, is a difference of about 50 gigatons of emissions, cumulative emissions between now and 2050. That's a lot of carbon that would be back into we have to be replaced by something. And it won't all be replaced by renewables. A lot will be replaced by fossil. There's no other way to avoid it. So keeping these plants is very important. And unlike what some people seem to think, this is not an economic challenge. If your objective is to have low carbon electricity on the grid, keeping these plants, whatever the investment is, and we looked at this jointly with the International Energy Agency, long-term operation of existing nuclear power plants is the absolute cheapest way to have low-carbon electricity on the grid. It's not even really that close. You can look at wind, you can look at solar, you can look at all these other options. Nothing is cheaper than keeping the existing plants in operation. So there's no technical argument to shut these plants down, and there's certainly no financial argument to shut these plants down. It's only politics, and fortunately, most countries have avoided that. In California, in the U.S., California has been a very I don't want to use the word anti-nuclear, but very adverse environment for nuclear for a long time. California has now turned around. One of the plants in California, Diablo Canyon, was about to be shut down. The state said, wait a minute, we're worried about climate change, we're worried about energy stability, we need to keep this plant. So they are going to continue operating this plant, which was a big surprise to many environmentalists, I can tell you. But what we have today is not enough. We're going to have to build more. So building more large Gen 3 plants is going to be essential. You can see in this chart that will knock another 23 gigatons off of the emissions between now and 2050. And this is equally an area that has some controversy to it when you look at the analysis. And why is that? Well, it's because we in the West, Western countries, have been atrocious at building these plants. There are plants today being built in Finland, in France, in the United States. Those three projects in those three countries have experienced significant cost overruns and significant delays. And it has led some people to think that nuclear plants are just inherently too expensive to build, too hard to build, and therefore don't put your investment in it. We know that's not true. The NEA has done a lot of analysis on this, and we've looked at projects all over the world. And what we have found is that the reason that the projects in Finland, the United States, and France have had so much trouble is because the infrastructures around those plants were simply not prepared to build new plants. It has been 30 years since the last nuclear plant was built in the U.S. It's been about that long for the French. About the same in Finland. When you don't have construction over a long period of time, you lose your supply chain, you lose expertise in project management, the regulators aren't accustomed to new projects. You add that all up, you get problems. And that's what happened in all these cases. When you know what you're doing, it's actually pretty easy. In a good case where someone knew what they were doing, look at the UAE, the Baraka project. 4 reactors, all on schedule, pretty much at the same cost as projected in the first place. What was the difference? The difference was the supplier was Korea. And Korea has a very well-established practice system for building nuclear plants because they've been building nuclear plants continuously for the last 25 years. So they know what they're doing. And if you look at China, you look at Russia, you look at India, you don't see these giant overruns because they've been building plants consistently for years. So what we in Western countries have to do is to get back in the practice of building plants. And there you'll avoid these problems. Now there are people that think that it's too hard to get to build the infrastructure and the expertise to build new large plants. And that's one of the reasons that small modular reactors became so popular. There certainly was the belief that small modular reactors could be a game changer, not just because of the safety performance or the economic performance of the plants, but the fact that, at least in theory, you can build them in factory. We know how to build things in factory in Western countries. We know how to build airliners. So the question that people often ask is, why can't nuclear plants look like airliners? Why can't we just have them rolling off the assembly line hundreds at a time instead of these large stick-built projects that take a long time and are very complicated? Well, we'll see. That's the great hope that we'll be able to build these in factory, that they'll be much simpler to build and operate and deploy, but all that remains to be proven. But if we're successful, they can be a major contributor. And they won't just simply be a contributor for electricity. They'll also be a contributor for non-electricity applications. And one of the things that we are watching very closely is how these small reactors, which aren't just light water technologies, but are also more exotic technologies, molten salt reactors, high temperature gas reactors, fast reactors, can provide heat for industrial applications, heat for the steel industry, for chemical industry, to make hydrogen, or in some cases make clean water. All that's within the realm of the possible. And so we're going to be watching how these technologies are deployed over the next several years. And what we're going to see is not just one small modular reactor around the world. We're going to see lots of different small modular reactors. We count about 90 different technologies that are under some level of development. Some are very close to deployment, others are much further away. All different technologies, different sizes, different coolant temperatures, different applications. Possibility that some might even be mobile, some might be placed on ships. This is a really interesting one. You think about it. Think about the large cargo ships that go across the ocean back and forth all the time, carrying goods from manufacturing hubs in Asia, for example, to Europe and North America. There's hundreds of these ships out at sea on a continuous basis, and they're emitting CO2 every kilometer of the way. Replacing that with some sort of nuclear technology is something that's not really a new idea, it's really an old idea, because the thought existed back in the 60s to have cargo ships with nuclear power in the past. That idea is coming back using new technologies that people think will be much safer and much less prone to accidents. And I think that's one of the reasons that they disappeared in the 60s. So we'll see. So there's lots of different projects, as I mentioned. Many of these, if you look at this chart, you can see that they're all over the world. There's many in North America, there's some in Europe, there's some in Asia. So 90 different technologies. And while that sounds like a positive thing, I think that led to a little bit of a paralysis, because when policymakers and regulators realized there's this giant collection of technologies out there, they're not really sure what to do with them. They're not sure how to prioritize where they put their efforts and resources, including investors as well. Not sure what to do with that large number. So one of the things that we've been doing at the NEA is we put out what we call the NEA SMR dashboard. So if you go to our website, you can download this. So the first edition of this came out just a couple of months ago, and it shows 21 technologies that are under development and under design today, and evaluates them based on how close they are to deployment using these factors: licensing readiness, available financing, available supply chain, public engagement. Do they have a fuel that's ready to roll? Have they started siting processes? So if you haven't done all these things, you're not really on track to deploy anything. So that's what we use as a measuring stick. And for some of the technologies, they're very close to deployment. We can certainly see that some of them will be ready at or before 2030. For other technologies, they're much further out. So the next edition will come out in July. We'll have covered 41 technologies, and then at the end of the year, we'll issue a final report that covers all 90 technologies. And our aspiration is to put the entire thing online, to have it continuously updated next year. So watch this space, but feel free to download the first SMR dashboard. So we put all this together, and you can see, if you look at the dotted line there, if you put all these pieces together, you get really close to the tripling. So while I can't tell you I think that this is going to happen, it is certainly possible for it to happen. It is possible to build enough, to keep enough of the existing capacity online, to build Gen 3 plants, to build Gen 4 plants, to make nuclear available for process heat and other applications. You put it all together, we could triple nuclear capacity. It is in the realm of the possible. However, if you look at where we look at the plans that people have in place, even the tentative plans, this orange part here shows you what the gap is. And this is a gap that is not going to be easy to close. It is possible, but it's not going to be easy. But if we don't close that gap, I think you realize that all these scenarios we've talked about to try to meet the climate challenge, we're most likely going to fall short. And that's not just because I think that nuclear is the right answer, and it certainly is not the right answer for some countries, so I'm not going to say this is for everyone, but globally, if we don't have this kind of capacity online, we're not going to be successful. So one of the things that we are looking at the NEA is how do we close that gap? And closing that gap, in my view, really comes down to four major areas where we have to put attention. And most of these are policy issues, but some of them are technical issues, and I'll go over them very quickly. So let's talk about the industrial challenges. The industrial challenges are actually quite significant, and it really relates to looking at what has gone wrong in the past. Can industry actually execute projects? Can they be successful? Can they bring these new technologies to the market on schedule and show that they can build them on a continuous basis without these giant cost overruns? That's a big question. Until they prove it, no one's going to believe it. Operational models is another one. These small reactors are very different from the large reactors of the past. If you build a large reactor, you have to have an operator that is equipped to be licensed to operate this facility with a large number of staff in order to operate safely. With small modular reactors, you might have dozens of the same reactor in different locations. What's the operational model for that? What about autonomous operation of these reactors, which some people are talking about? There's a lot of discussion about what operations might look like for these small reactors, but no one has really clarified that yet. So industry really has some work to do to say, how are we going to do this? How's this going to actually work? And it's not, to me, it's a non-trivial question that needs to be answered. And I've already mentioned supply chain. Supply chain is a big problem. When in the U.S., when we were building the AP1000s that Holden is now talking about, there was a lot of confidence that the supply chain was in place. I remember seeing a computer program that Westinghouse had, this was years ago, and they had for every part in the entire plant, there was at least 3 suppliers, and there were actually prices built into the model. And they were very confident they could deliver these parts on schedule. And the suppliers felt that they could deliver on schedule. But when the time came to actually make the parts, some of the suppliers couldn't do it. They either couldn't make the quality standards, or they couldn't create the paper trails. They just didn't know, because the last time they built parts for the nuclear industry had been 20, 30 years ago. So even though people sometimes think they can do things, sometimes it turns out they can't, and that leads to significant problems and cost overruns. So supply chain is a major issue, and it's one that we're working on a lot. Another issue, our friendly neighborhood nuclear regulators. Now, I feel comfortable talking about this because I'm a former regulator, so I'm in the club, so I get to point fingers and say, not good enough. Regulators have to adapt to new technologies. They have to recognize that the small modular reactors, particularly on non-light water technologies, are not the same thing as large light water. Just not the same thing. And if they treat them like large light water, we always might as well stop right now and stop wasting our time, because there's no point in building these advanced technologies if regulators are going to treat them like old technology. And I hate to say that in some countries, I think that's likely to happen, at least in large respect. So regulators have to get with the program. They also have to think more globally. So small modular reactors might be built in large numbers. And I use the analogy of the airline industry. So Airbus builds Airbus 320s. Not every individual 320 has to go through regulatory review in the country it operates in, right? There's an assessment, of course, but there's not a detailed regulatory route. You don't have to get a license for each individual aircraft. That's what we're going to have to see the nuclear industry look like in the future. We're going to have to look more like the airline industry than we do today. And that's a big change for regulators, to think more globally. That doesn't mean we're going to have one global regulator. That's impossible. I don't think it'll ever happen. But regulators can certainly work together to remove some of these barriers. And regulators have to accept new paradigms. I talked to a head regulator not too long ago, and we were talking about small modular reactors, and I made mention of the fact that in the United States, some technologies are seen as not requiring any off-site emergency preparedness. All emergency preparedness is within the site boundary. And off-site, no one needs to worry about. There's no need for sirens, there's no need to evacuate, there's no need to shelter. All that goes away because the technology is so safe. And this regulator from this country, which I will not name, told me very clearly, in his view, emergency preparedness is defense in depth. You will always have emergency planning zones. They will always look about what they look like now. And I was thinking to myself, if I was a small modular reactor vendor, I wouldn't even come to your country because it isn't worth the time. So regulators have to really, again, they have to recognize that these are very different technologies, different requirements, different approaches. There's also some very important, more general policy and market issues. Our electricity markets don't work. In some places, they're completely broken. Think about this. So we have electricity markets in some parts of the world where routinely electricity prices go negative. If you have a market where electricity prices go negative on a routine basis, that's not really a market anymore. I'm not sure what it is, but it's not a market. And on top of that, the markets, nowhere do the markets reward you for having low carbon technology. Nowhere do they reward you for reliability. Nowhere do they reward you for dispatchability. This is not the right thing for the future. We have to reform the electricity markets, and we have to do them as soon as possible, because if we don't do it, we're not incentivizing people to do the things we want them to do. Governments have to also recognize that if you're going to deploy new technology, that sometimes private sector is not really going to be able to take the full cost of doing a new technology and take all the risk. It makes no sense for us to drive utilities or investors or vendors bankrupt because we're trying to deploy new technology. Governments have to step up, governments have to protect and facilitate this if they want to have these technologies available for the future. And financing in general is a major issue. It's very, very difficult to finance first-of-a-kind technologies, particularly innovative reactor technologies. It's hard to get the money commercially. Governments are going to have to step up. Finally, I'll talk about infrastructure challenges. You may have heard about the HALEU problem. How many of you have heard about the HALEU problem? Very, very few of you. Okay, here's the HALEU problem. So current nuclear power plants operate using enriched uranium that's enriched to about between 3 and 5% uranium-235. That has been the case for many decades. Some of these new technologies require material that has been enriched up to about 19%. There is no 19% material. There is none. We don't have it. And interestingly enough, and you'll find that you'll appreciate this, that the vendors, when they first started their projects, thought they could get the highly enriched uranium from Russia. That's what the plan was. The plan was to get it all from Russia. Well, can't do that now, right? So where's this coming from? And today, the people who make enriched uranium around the world, they don't see the market yet. So they don't want to put the millions of dollars and millions of euros into building the capacity to make high-assay, low-enriched uranium until they're sure there's a market. So it's a chicken and egg problem. The only way to solve this is with the government. Again, governments are going to have to step up. They're going to put a lot of money on the table to make this happen. Codes and standards is a really tough one. It'll probably never really get solved, but I list it here for completeness. We have a plethora of different codes and standards to do almost the same thing around the world. It's a stupid thing to have done to ourselves, but it really grows out of the origins of the nuclear sector. Completely different from the airline industry. If you look at the codes and standards for the airline industry, it's harmonized around the world. It all looks the same. Completely different in the nuclear sector, and it's a big problem. And finally, human resources, and that sort of brings me back to all of you. One of the big problems I think we have in many of our countries is there are not enough people available who are coming into the sector to make up for the retirements that are taking place today. So we at the NEA have undertaken a variety of different activities to deal with this situation. And I'll just talk about them very briefly. One, we have formed the Global Forum on Nuclear Education, Science, Technology, and Policy. This is something that I find quite exciting. This is the first standing body of nuclear educators in the world ever. And that's kind of amazing considering that the nuclear industry has been around for about 70 years. The first time we've had a standing body. And so this group, which has been in operation for the last few years, is looking at a wide range of different issues. They bring universities, professors, and administrators from around the world in working groups to look at these different subjects: achieving gender balance, defining the future of nuclear engineering education, rethinking the relationship between nuclear energy and society, revitalizing innovation, and rebuilding expertise in nuclear law. So these people are working very hard on this right now. It's a very exciting activity. And one thing that has come out of this is that we are holding what they call Rising Stars Workshop, Global Forum Rising Stars Workshop, which will be held in September of this year at MIT. And this little box here will show you how to apply for that if you're interested. If you're selected as a Rising Star, you will have a free trip to Boston to participate in this and to work with people from around the world to develop careers in particularly academic careers in the nuclear area. This is not available to everybody. It is for women. So guys, sorry, you can't apply. And this will include a lot of discussion about career development and mentoring, and it is part of a larger effort that's going on around our member countries to deal with gender balance, which I'll talk about again in just a moment. Another area which we've talked about with your government is called the NESTIN framework, Nuclear Education Skills and Technology Framework. This is really a series of research projects that are not just research for the sake of research. It's very practical, very real-world problems that need to be solved. In this case, the people who will be working on these problems are university students. So for a NEST project, it takes at least 3 countries to agree to do a project, and then universities in their countries can identify students who will become NEST fellows and work on these technologies. And as example, we have a project in Japan looking at decommissioning, using robotics for decommissioning the Fukushima Daiichi site, which involves about 4 different countries. There's a project that's co-hosted by Canada and the US on small modular reactors. There's one in Italy dealing with medical isotopes. So there's about 7 different projects, and I think about 200 fellows currently in the program. So we'd like to see Poland become part of this. So I've had a conversation with your government. Hopefully that will happen sooner rather than later. We'd love to see it happen. Final thing I'll highlight is we are doing work in gender balance. This is something we're quite proud of. We did a survey of our member countries' organizations. We got data from 47, I hope I have that number right, 47 organizations of our member countries that are nuclear organizations. And we asked them a lot of detailed questions about what is the state of women in your organization? What level of management are they? How much are they paid? Are they giving facilities to help them build management and leadership careers? So we gathered all that information. And then we also, in addition to that, surveyed 8,000 women around the world, where we get qualitative information about the experiences they've had, any issues they've had regarding their nuclear careers. We put all this together and we found that there's a serious problem. And the problem is that consistently only about 20% of the science and technology workforce in the nuclear sector is female. And that's just too low. We need to do better than that. And so we have issued this report, and it's led to an initiative that next week, and I'm quite excited by this, next week the OECD, the organization of which we're part of the framework, is going to issue a formal policy recommendation to correct the gender balance. This is the first time anything like this has happened, and it is not one of those high-level policies where we simply say, oh, you countries, you should do the right thing, have more women. It doesn't, it goes very, very deep in detail. So if you look at the report, and it's online, you'll see what the policy recommendations look like. They cover just about everything, from attracting more girls into science and technology careers, having programs to support women once they become parts of the industry, and to also encourage them to move in leadership positions. And most importantly, there's a huge amount of data that we will require from the countries to show what is actually going on. Because one of the things that was really interesting for us was when we started asking countries questions about what was the role of women in their organizations, they couldn't answer because they didn't have the data. From this point forward, we're going to have the data, so we'll know what's going on, and we'll be able to measure it and see if we're making progress. So I recommend you take a look at this. So I'll wrap up, and I want to highlight that meeting this climate challenge is not going to be easy. And what I often hear from people is, and you see this more and more these days, that the problem isn't really that we don't have enough energy. The problem is that we use too much energy and that we're too wasteful. And what we do needs to be adjusted to save the environment. And there's a lot of people that are making this case. And I think it's true. Yes, we could all give up our cars and ride bicycles to work. And if you go to some countries like the Netherlands, everybody rides a bicycle to work now, so they wouldn't miss it. But for me, that wouldn't be practical. And here's this young lady from Sweden, you recall, that famously took a sailboat across the Atlantic instead of using an airplane because it was better for the environment. If I took a sailboat every time I crossed the ocean, no one would ever see me. I'd be on boats all the time. I would never be in my office. It wouldn't work. And one of the things that I have seen hints about, which I find most disturbing, is there are people that think that countries that are trying to build a middle class, trying to raise people out of poverty, maybe they have to wait a little longer or be a little less ambitious because the environment can't handle having another country moving into the middle class. There's people that actually feel this way. My message to you is, if that is the message that we are going to give the publics, both in the OECD countries and in developing countries, that climate requires you to give up your life, give up your air conditioning, give up your car, basically give up Western civilization, they're not going to listen to us. They're just going to ignore us, and we'll have failed. This is a failure path. And so I believe that we have to give the public an answer that both saves the environment and maintains the ability to aspire to improving standards around the world for life and society. And I think, personally, in my view, and a lot of people agree with this, is that a cornerstone of making that happen is innovative nuclear technologies, along with other things, that make it possible for us to have economic growth, economic stability, social progress, while at the same time reducing emissions. I believe this is possible. Obviously, if it's going to happen, we have a lot of work to do, but if we are serious about this climate crisis, we don't have a choice. We have to do it. And if we are not successful in making these technologies practical and we don't deploy these nuclear technologies, it's not a failure just of the nuclear sector. It's a failure for our entire generation to have met a challenge that was put before us and that we simply didn't get it done. And that's something that I think we have to try to avoid. So with that, be happy to answer any questions. Thank you very much.
Thank you very much, Director Magwood, and we are ready for the Q&A session. You can ask questions both in Polish and in English. If you would decide to ask a question in Polish, we'll translate the question for you. If you would rather not speak English in public, so I would like to make it accessible to everyone. Are there any questions?
At the beginning, you mentioned goals to reduce our emission. Do we reach them in any of the countries in the organization?
Didn't quite catch that. Ask that one more time.
At the beginning, you mentioned goals to reduce emission.
European Commission. Reduce emissions.
Reduce emission. Do any of the countries in the organization reach that goal? Or
It's the last part I can't quite get. Did you?
do any of the countries reach that goal, or is it?
Okay. No. So there are some countries, certain. When I say no, I'm looking really at the large industrial economies. I'm sure there's some small countries that have made a lot of progress, but for the large countries with industrial economies, none of them have really reached the target. The closest that, from what I have seen, is probably France, because France is 70% reliant on nuclear. And they're the only ones I think they're close to their climate targets. The others are quite far away.
Okay, any further questions? Okay, so let's start from the back and then we will move forward.
It's the consequence of sitting close.
Thank you for the lecture. I really liked the idea of that radar tracking progress of new technology. Probably you're aware that in Poland we try to experiment or have ambition to experiment with small modular reactors, at least with 2 or 3 technologies. So if you can give us your insight into what you think are the 3 most promising small modular reactors, and maybe you have your own personal black horse in the race that you think should win that race.
Yeah, this is one of those questions they teach you not to answer. But let me put it this way. Clearly, the technology that is most popular right now, and which clearly there's absolute confidence that we can deploy on a reasonable basis, is clearly the BWRX 300. I don't think there's much question about that. It is not as advanced as some of the other technologies, but it is one we know we can build. And I think there's a lot of confidence in that. So today, there are utilities that have pretty firm plans. In fact, in the Canadian case, they've already started clearing ground to build the first one. So in Canada, the United States, and a few other countries, there's pretty clear plans to build this technology. Among the small modular reactor technologies, that is clearly leading the pack right now. There are other technologies which will be available and competing with that, but that's one that seems like has gotten a lot of attention. Another technology which I think is going to eventually get more attention is the technology of the high temperature gas reactor from X Energy, because the fuel exists right now. It's not a research issue. I know that for a fact because I started the program that developed the fuel. It took a long time, but it's done. We know how to make. It's really a remarkable story because I'd say 15 years ago, people didn't believe that we knew how to make TRISO fuel with consistent quality. Today, we absolutely know how to do it, and that's a game change. And so we know how to do it now. We know how to make the fuel, and if you can make quality TRISO fuel, the safety case of the reactor speaks for itself. And so that's one that I look at. There are certainly others that are out there that are in the same range, but those are 2 that I personally have a lot of confidence in.
Okay, further questions? So there were some in front.
How much smaller is the capacity of the How much smaller is the capacity of the smaller nuclear power plants that we were talking about, and what can they power? Like a settlement or just a family house?
There is a vast range. There are reactors that are in the hundreds of kilowatt size, so very, very small. Those are usually heat pipe reactors that would be used in remote locations for different purposes, usually industrial purposes, and everything between that and up to about 300 megawatts. So everything in between, and there's just lots of different technologies of different sizes.
So it isn't really practical to power a small settlement with such one?
A small satellite?
Settlement.
Settlement. Oh, yeah. No, there's definitely plans to do that. In particular, the Canadians are very interested in this. In Canada, there are these remote communities that import fuel oil for diesel generations in order to have electricity. And this not just makes emissions, but it's incredibly expensive to bring diesel oil daily, daily. In fact, they fly it in by air because of the conditions. Incredibly expensive, and they would love to replace that with a nuclear facility. And there are different technologies they're looking at to do that. And these are technologies that theoretically could be right next to a small community and operate for years without being refueled and provide electricity and possibly heat. So this is something that is really on, not just on the drawing board, but people are really aspiring to do in the next few years.
So it is theoretically practical to power a settlement of 400 people with a nuclear reactor?
Possible, yeah.
Okay, and may I ask one more question? What are the challenges in making the nuclear-powered ships more available? Because as far as I know, there are really few of them, but there are lots of submarines.
The ships? Well, we don't have any nuclear-powered civilian ships today, except the closest we have today are, in Russia, they have these nuclear icebreakers. I've been on one. They work pretty well. But I think that that's not the technology that we would use for ships in the future. We'd probably use something closer to these microreactors that I mentioned earlier, the heat pipe reactors. So they're very simple, very easy for a crew to operate. It wouldn't require a tremendous amount of expertise. That's the direction I think people would want to go in. So we haven't done that yet, but that is something that people are definitely talking about.
So the main challenge is that making the reactor smaller, because the current one do not fit on the practical ships, right?
It's not hard to make them smaller. It's a question of what is the right technology for the application. You can make a nuclear reactor small enough to be on the back of a truck if you want, but does that meet your needs? And in some cases it might. The military is looking at some technologies that probably are truck mounted. They could be taken to, say, a battlefield if they want to provide electricity for a forward base. That's something that people are looking at, and that may actually happen sooner rather than later. So yeah, you can make them quite small.
Nice, thank you very much.
Thank you.
Okay, so first I will introduce a topic to my question. From my lectures on nuclear energy, I remember that at current consumption rate, our uranium resources will last for 300 years. So if we so drastically increase our consumption, this will obviously decrease the time for no. My question is, do we have a solution to a problem of scarcity of uranium on our Earth?
Well, I don't think uranium is scarce.
Well, maybe scarce is wrong problem, but we have to look
300
deeper.
Years, 300 years is a long time. But you're right. I mean, that's the estimates usually revolve around 300 years for the current pace of consumption. If you triple the size of the nuclear fleet globally, that comes down to 100. If you believe that number. Several things about that. First, that number is mostly focused on what are today economic resources. If you are using that much nuclear electricity, there's other resources, other mines that have been shut down because they're not economic that you would probably reactivate. So that would probably buy you more time. In addition, there are technologies for seawater extraction of uranium. They're today not economic, but if you have that situation, you would probably do it. So there's a lot of things that would happen. But obviously I think that, and maybe this is the point of your question, we absolutely should be looking at recycling these materials. If you recycle the fuel that we have, you have enough fuel for more than 1,000 years. And I, of course, believe we should be doing that, but that's still a conclusion that needs to be reached. We're doing actually a study, an expert study looking at the state of the art of partitioning and transmutation and recycling technologies will be coming out later this year. that will look at where we are and what we need to do to make this technology more commercializable. But right now, today, very few countries are doing reprocessing, and that's because of this conventional reprocessing using PureX technology is exactly the same technology that one would use to extract plutonium to make nuclear weapons, and that makes people very nervous. So what we need to do is to move to a technology where you can't extract pure plutonium. Instead, perhaps a mixture of actinides that can be used in fast reactors. And so something like that might be the answer. But today, we're not really worried about uranium supply. It's not that scarce at this point.
And another question, do these simulations regarding increasing the nuclear power as a way to tackle the global warming problem include also thorium breeding reactors?
Oh, some people are certainly talking about that. Not everyone. Breeder reactor has a bad name because it sounds like a proliferation issue, but there are clearly people looking at fast reactors. I was just in Japan recently, and they are looking at sodium-cooled fast reactors as a big part of their future. This has been a Japanese dream for a long time. It went away for a while after the accident in Fukushima Daiichi. It's come back again. And so they're now putting big investment into that. So there are definitely countries going to be looking at that. And in a large respect because of what you just mentioned. Even if there's a lot of uranium in the world, if you're Japan or some other countries, perhaps you don't want to be relying on that supply. You want to have your own internal capacity to make sure you have fuel for your reactors. And recycling would make a lot of sense for that in that case.
Okay, thank you very much.
Thank you.
Okay, Szymon Malinowski. I had a question which was partly answered here about recycling of the nuclear fuel, but I have a more specific question. Are some new activities being undertaken just what is the perspective for this new activities? Since recycling is a great thing and it's in accordance to many activities we are taking, and we know that only a small fraction of fuel is being used. So could you elaborate more about international actions or research on the recycling?
Well, there is research. There are several countries looking at how they could do recycling. But the real issue is there's no real driver for it right now. As I just mentioned, there's still lots of uranium. So no one's worried about the uranium supply. And the current technology not only has proliferation issues that people talk about, but from a nuclear waste disposal standpoint, doesn't really do that much for you in terms of the final repository, because you still have the same kind of heat generation rates you would have in just this direct disposal of spent fuel. So the repository looks the same. So we need to move to an advanced technology that really reduces the toxicity of the nuclear waste, reduces the level of plutonium and other actinides in the nuclear waste, and that would be worth doing. But we don't have that technology because we haven't been doing the research. And we haven't been doing the research because people worry about the proliferation issues. So I think we're probably not going to see a lot of activity in this area in the near term. Countries are much more concerned with just getting this next generation, the small reactors off the ground. And if we need reprocessing and recycling in the 2050 time frame, most countries think we'll have plenty of time to deal with it then. So right now I don't see an awful lot. I see really long lead research, but not the kind of investment you would need to actually deploy a new technology today. And simply because they don't think there's no driver for it right now. And also, I'll also make note, if you were to build the current technology recycling PureX plant, they're really expensive. It's probably a $30 to $40 billion investment to build a plant from scratch, and that's probably conservative. So that's something not everyone's signing up for right now. This is not a very gender-balanced Q&A session, I have to say.
What about nuclear aircraft? Because I am aware that there were plans for it back in the day, and there was one built, despite it wasn't being powered by the reactor. and could they possibly be used in the near future?
Oh, that's a really interesting question. Yes, we had nuclear airplane program back in, this goes back to the 50s, where this was going on. And I think that almost everyone I've talked to about that thinks it was a bad idea almost from the very beginning. So I don't think you're going to see that. I think more likely for aircraft, if there's a nuclear connection, there's a possibility of making synthetic fuels using nuclear reactors. That's a more likely path than actual nuclear airplanes. I also don't think you're going to see nuclear rockets for liftoff. That was another idea that no one likes today. But there's a tremendous amount of interest in nuclear rockets to be used in space. And in fact, if you want to go to Mars and you're not using a nuclear system, don't go. And the reason for that is it will take you so long to get there that you'll be exposed to so many heavy ions in space that by the time you get to Mars, your mind will be so deteriorated you won't know why you went there in the first place. So don't go. Only go if they give you a nuclear rocket. But nuclear airplanes, no. I don't think that's coming back.
Thank you. I would like to ask about situation in Poland. So as far as I know from the lectures, for now the same rules apply for SMRs and large nuclear reactors. And do your agency or you, have you met with Polish authorities, and is there a path to changing this? Because as far as I understood you, we have to change this for SMRs to be realistic.
I think the reality is that the regulator in Poland is working from very high-level standards that apply to both Gen 3 technologies like AP1000 and to SMRs. How you apply those is where it becomes important, because there are certainly aspects of small modular reactors where there's exemptions from those general rules. And that's where the judgments come. So they have not gotten to that point yet. They have not had that conversation. It's really just getting started. And I don't think that is, I don't know, it will depend on whether there's an application that comes before them, but it is not their highest priority right now. They're putting some resources into it. They have a small number of people who are now looking at small modular reactors, but it's much, much smaller than the activity on the Gen 3 plants. So they have not gotten to that point yet. And from the conversation I had, I'm actually pretty confident that they will recognize that there's a difference between the two.
Hello, thank you very much for your presentation. It was really fascinating. I have one question, because you talked a lot about nuclear power as a solution to climate change. And I see one challenge here, and I was wondering what's your view on it. Climate change is going to mean that there is higher risk of severe droughts and severe floods and other extreme weather events. This, as far as I understand, could potentially pose a threat to reliability of nuclear power plants, for example, cooling them from rivers, etc. So from the regulatory standpoint and industry standpoint, is this a challenge, and what are we doing to mitigate it?
Really excellent question. We did some studies on this, and I agree with you. I think there is a threat that's out there. It is a very long-term issue for most for most of the world, and I don't worry as much for new plants, because I think if you're building a new plant, you take that into account when you do the siting. The question comes in more to play for some of the existing plants that might be in areas where it isn't so much that there's not enough water, but that the water temperature might be increasingly high, and that could mean the plant will have to go offline more often. So we're starting that. We've actually seen that in some countries. But I think in the lifetime of most nuclear plants, I think this is still manageable. But longer term, it's something we're going to have to pay a lot of attention to. And some of the technologies don't require nearly as much water as the traditional light water reactors. So I think they'll be more attractive as we go forward into the future. But that's something we're paying attention to.
I have a related question to the water problem. we have the general issue of climate change, which affects much more the global south, let's say, than the north. We also have we are experiencing not only the increase in temperature, but also lack of fresh water. And is there any project at the moment that you can see which would apply the small nuclear reactors to desalination? And where is it happening?
It's not, there's no projects where anyone has actually implemented anything yet or started construction, but there's a lot of conversation, particularly in the Middle East, about this. UAE, Saudi Arabia have talked a lot about this. I think the Chinese have some research projects looking at this. My projection is that 10 years from now, you're going to see something really substantive in that area. I think the lack of clean water in certain parts of the world is a dramatic problem. Clean drinking water, and the desalinization is going to be a big part of that answer. And I think it won't just be in places like the Middle East. I think it'll be in places like Europe and the United States. So this is coming. I absolutely agree with you, but it hasn't happened yet. But I think particularly as we get drive closer to net zero, you're not going to have any choice because it takes a lot of electricity to desalinate, and right now people are using fossil fuels.
If this problem can be solved in Africa, it might be a solution for the big migration north, yes, of people that escape from drought-affected regions.
All these things are always connected. I mean, if you're building reactors in Africa to deal with desalinization, you probably have enough industrial infrastructure to give people jobs to keep them in their home country. So I mean, it all goes together. So it isn't just a matter of water. It's a matter of having opportunities, having possible careers and education. Those are the things that are going to be important in the future. And really, for a lot of these countries, there's really nothing more important than educating. And I think countries like Poland are really good examples of countries that do offer education opportunities to people from developing countries. We need to do a lot more of that. That's how you solve the problems.
Considering there exist small reactors powering submarines or aircraft carriers, why it is so difficult to develop civilian ones? Is it a question of technology, safety, or just regulation? That's the first question.
Lots of stuff in that one. I guess I look at it this way. Naval reactors are extraordinarily robust, amazingly expensive, and designed for a very, very particular purpose. There has certainly been people who have made the kind of comparison you've made, that we know how to build these small reactors and submarines, why can't we just use that same basic approach to build these land-based reactors? There was actually a project in the US from a company called Empower. That's kind of what they were trying to do. They were trying to kind of adapt the technology in a way for commercial purposes. It didn't really work out very well. I think for commercial applications, you need something very different, with different safety performance, different cost structure, and I think we're seeing that. I mean, it's happening. I wouldn't say it's hard because of the technology. I think it's mostly hard because of the cost and the financing. If you look at the NuScale technology, for example, NuScale is everything we say we want. The only issue with NuScale is it costs a lot. If it weren't for the cost, you'd probably see them all over the place by now. So I don't think the analogy really holds, because military reactors are just different animals. They really are, and very, very expensive. You would be shocked to see how much they cost.
I would like to ask a question regarding a bit more of the regulatory issues and trends within them, because sometimes it happens that countries which are newer democracies and are trying to catch up to the established countries put in place policies which are way more progressive in some aspects. Is it something that happens in the nuclear energy region or not at all?
Not exactly. There's not a lot of experience with countries really putting together full regulatory infrastructures from scratch. I think if you look at what's happening with Poland right now, for example, Poland is drawing from expertise and experience from a lot of different places, from the United States, from France, training of people who go to places like Canada to see how inspections are done in Canada and bring that knowledge back. So they're not doing anything revolutionary. They're really trying to go state of the art. So what are the best regulators doing now? And they're adapting that for here. But it won't. I think the end product won't be dramatically different. What we more commonly see, unfortunately, are countries that essentially rely on their supplier to tell them what to do, tell them how to build a regulatory infrastructure. This is certainly the case with Bangladesh, for example, which relied very, very heavily on Russia for the training of all its people, including the regulatory staff. So they're very reliant on that expertise and to do things that way. That's not the way I'd prefer to see countries do this, but the problem is that countries are in a very, very big hurry to build plants, so they don't have time to do it what I would call the right way, which might take 20 years of building up expertise. So you're seeing these countries take a bit of a shortcut and really relying on a supplier to tell them, here's how it's supposed to happen. But we aren't seeing. I wouldn't say you would see innovation out of the newcomers. I'm not seeing that.
Hi, thank you for the presentation. I would like to ask about the supply chain you've mentioned before. So basically, with many nuclear reactors being planned to build, especially in Europe and exactly in Western countries, I would like to ask about those long lead items, especially these forgings of huge reactor pressure vessels, as well as for, huge nuclear reactors, as well as for SMRs. So my question is, what are the possible solutions for the turtleneck in this industry? Because there are not that many suppliers of such forgings, and what are the possible solutions to this problem?
There's no easy solution. The only way to get better at something is to do it. So we're going to have to start building parts. We've had some countries talk about the possibility of picking some key components and having the targeted contractors build those components, even though there's not a project yet, just to show that they can exercise the systems and see if they can meet the quality requirements. There's just no simple way to fix it. And even more difficult, it's hard to know where the problems are. So this is why I listed it. This is a big issue for us, and as of right now, I don't have tremendous confidence we're going to solve that problem easily. It may simply require building nuclear power plants and going through the pain of proving that these systems can be put in place and these contractors can build these components. Some components, however, are probably not going to be built in country. They'll probably be built by experienced people. For example, a lot of the larger forgings that are used in the West come from Korean and Japanese forges, which are very well practiced and very high quality. So those are never the problem because we get them all from Japan and Korea. It's usually the smaller parts, valves and pumps and issues and some I&C issues. That's where the issues usually pop up, not the big components.
All right, thank you. And the second small question: do you believe that there will be a first SMR in 2028 in Canada or US?
2028 or so, probably close. That they're aiming for 2028. Whenever you're doing first of a kind, it's always dangerous to say you're going to meet this exact schedule. But if it slips, I don't think it'll slip a lot. I think it's very controllable. I think there's good people involved with good experience. So I think they can pull this off. But I'm not going to bet on 2028. If it ends up being 2029 or 2030, I wouldn't be shocked by that at all. But it'll be pretty close to 2028.
Should we treat nuclear energy just as a transition to the fully reusable green energy, and in the meantime, should we just hope for a major breakthrough in this technology field, so third world countries can afford this energy?
Give me the question one more time. I'm not sure I got it all.
Should we treat nuclear energy just as a transition to the fully reusable green energy, and in the meantime, should we just hope for a major breakthrough in green energy, that it will be affordable in third world countries?
That's almost a political question. What I would say is that if you build a nuclear power plant today, it's going to be around well into the 22nd century. If you think that's transitional, okay. I don't see it that way. I honestly think nuclear is here to stay. I don't think it's going anywhere. I think it can operate in a manner that makes renewable technologies more effective, because it provides a dispatchable resource that can fill in the gaps, which is really desperately needed right now. Because if you look at what's happening with renewable energy often today, it's backed up by fossil fuels. It's backed up by gas for the most part. And what a lot of people don't realize is that if you're operating a significant amount of, say, wind power or solar power, you're going to have parts of the day where you're going to have excess energy. You can't use it all. You have to just sort of dump it off to the grid. But you're also going to have periods where you're not getting enough, and then your gas turbines kick on and make up the difference. But the gas turbines aren't just sitting idle. They're not just off. They're actually running at very low level. So they're constantly making CO2 even while you're getting high wind power. So you need to have a technology which is dispatchable, that can make up the gaps in renewables. And perhaps there'll be a storage solution in the long term that makes sense. The ones they've talked about so far don't make sense. But perhaps there'll be a storage solution where you can store the renewable energy, and maybe you can make this more economic. But my guess is that that's not going to work out very well. My guess is you'll probably still need to have a dispatchable resource to make the renewables make sense. So the short answer is no, I don't see this transitional.
You eventually used the word political, and it seems to me that in these days the issue of nuclear energy is a political issue as well, to a large extent. I would even say worse, that it's an ideological issue. For some unknown, difficult to understand reason, some countries think quite opposite to what you present here. A very good example is Germany. Germany just decided to shut down their nuclear power plants. What the American government is going to do with that? Not all the countries in this world share your view. For example, China is quite reluctant. In other words, they got huge deposits of coal that they would still like to use. They obviously, better than me, they must have some nuclear power plants, obviously, but they want to give up all the other sources of energy. So looks like there is a conflict here. How this political conflict the U.S. government is going to resolve?
Well, first, I don't speak for the U.S. government. I don't speak for the U.S. government. I'm not a U.S. government official anymore. But I think the way I will look at your question is that every country has to make a decision for itself, and there's lots of inputs that go into a decision on energy supply. Some of them are economic, some of them are technical, some of them are philosophical and ideological. And one of the things that from my home country, there's very rarely an ideological aspect to energy decisions. It's very pragmatic. If you want to build a nuclear power plant and you can pass regulatory review and you can find the money, you can build a nuclear power plant. No one's going to tell you you can't do it. In some countries, the decision goes all the way up to the prime minister or the president, which is inherently political. You can't avoid that in those kinds of systems. So every country handles this differently, and I trust that these countries know what they're doing. Sometimes I look at what these decisions and I say, it's not going to work. They're going to, and what you often see is that when countries will make decisions that on one hand, they make the decision saying they're being green, but in the background, they're burning a lot of coal and gas and they're importing electricity from other places. So, every country has to make its own decision. So I don't think any other country is going to tell them, the U.S. government or France or anyone else is going to tell other countries how to design their energy policies. But if they make commitments on the international framework and they say they're going to reduce emissions to net zero by 2050, we'll be able to see if that's happening or not. And if it's not happening, I think they're going to hear about it from their colleagues. But you can't stop people from making decisions on whatever basis they make decisions on.
We have time for last two questions, and they're already queued. So one is over there, and one is here on my side waiting. So we have no more time for questions. I'm sorry. So now the last two.
Okay. So I would like to ask a question about the cost technology part of the matter. Some time ago, I heard about the idea of reusing coal plants. As the big part of the cost of building nuclear parts is the whole infrastructure of cooling, turbines, also the grid lines around to connect it with the whole grid. There was this idea of reusing coal plants, simply putting like different heat source in the system. And what's the work, what's the action, and what's your view or maybe perspectives on the matter?
Well, I guess I'll give you, my personal view based on what I know is that you're not just going to replace the heat source and use everything else. It's just not going to happen. But what you can absolutely do is you can use a lot of infrastructure, particularly the electrical infrastructure. So you can, if you use a site that has a coal plant and you build a nuclear plant there, you don't have to build new transmission lines. You have access to the same kind of water resources. I mean, some of it might have to be upgraded. But mostly you can use that infrastructure. You can use a lot of infrastructure. You probably can't use all of it, but you can use a lot of it. And that makes complete sense. But that's not the same as just simply replacing the heat source and using everything else, using the turbines or whatever. I don't believe that'll happen. I just don't think that's going to be the case. But siting at existing coal plant sites, that's something people are really interested in doing. Because building transmission lines is actually harder than building a nuclear power plant in most places. And if you can use the existing transmission system, you're going to want to do that.
So firstly, I would like to thank you for the lecture. I found it quite interesting. And while I was listening to it, a question arose in my mind. Do you have any solutions ready for the security issues that may arise? For example, around the introduction of this small modular reactors, because if, for example, some terrorist group seizes a stock of enriched uranium, well, I think all of us can imagine what could possibly happen. Then it would be disastrous, to put it short. And I think that for example, this uranium-powered cargo ships, which I think that are a very interesting idea, may still remain niche because you won't risk putting enriched uranium on a ship that can be seized by pirates, for example. And my question is, do you have any solutions for that, or you think that it's just another barrier that you will breach somewhere in the future?
Very, very good question. I'll give you a couple of answers to this. First, the most important thing to note is that the enriched uranium that would be in any of these systems could not be used for a nuclear weapon. Just wouldn't happen. For nuclear weapons, the enrichment levels more like 90% and usually higher. So 19.9% is not going to get you a bomb. And that's why it's 19.9%. Anything below 20%, anything above 20% is in a whole different regime, because people do worry about people getting access to that material. But at 19%, you're not going to be able to use it. But there is a real security issue. If you have all these small reactors, let's say they're in remote locations, some might be without personnel, just autonomously operating. What is security infrastructure that goes with that? Nobody has an answer for that. There's a lot of people who think this is not a problem because you can do the technical analysis and show that under the worst case scenario, nothing really bad can happen. If someone tries to blow it up, nothing really bad happens. But that's really silly, because if someone were to actually get hold of a remote reactor and damage it in some way, the public reaction would be so adverse that it might as well have been a nuclear accident. And so I don't see how you deal with that. So this is an active conversation that people are having. They're talking about it, and that goes with the shipboard or other issues that might come up in the future. So I do think the issue about security is one that we have to deal with, particularly if you have these remote reactor situations. Personally, I'm much more comfortable with having small reactors in a large, secure environment like a big industrial site or a nuclear power plant or something like that, as opposed to just being out there all by itself. But that's something that we're now working on, but not because of the enrichment rate. That's not the issue. The issue is more what's the threat of a radiological incident if you have a reactor that's out by itself, but not the enrichment radium. It's not really an issue.
Let me close this meeting by an observation that we had some audience members that tried to sneak in incognito at the very beginning, but I'm going to expose them now. Ladies and gentlemen, we were accompanied by the rector of the University of Warsaw, Professor Alojzy Nowak, and the vice rector, Professor Ewa Krogulec. So thank you for being with us. And I would like to thank Director Magwood for this entire meeting, which we saw provoke lots of questions and lots of meaningful answers. And I hope that everyone stays tuned to the developments in nuclear energy and the regulations. So, Director Magwood, thank you very much.
Thank you. Thank you.